Yeah, Hello everyone. I'm Changhong LINGHU from Zhejiang University, Professor Jizu Song's group. Today my topic is universal assembly grapher with massive and selective capabilities for multi-scaled arbitrarily shaped objects. I will begin with the introduction and motivation, and followed by the research content. And finally, I will give a summary. So let's begin with the introduction and motivation. So grouping and manipulation of objects are fundamentally challenging in tasks for robotic systems since those target objects are of different geometries and at different scales with different quantities, and sometimes even with certain special requirements. For example, in the assembly of micro LED chips, we need to group large number of LED chips in a massive way while print them onto the receiver substrates with a certain pattern. So a universal solution for the graping is very challenging. And when talking about graping, graper, we usually will think about the system, machinery system mimicking human hands. This kind of multi-finger robotic graper is very deleterious, but very complex at the same time. They entail the integration of a large number of sensors and also require complex algorithms to control the graper. On the contrary, the one-finger graper, one-finger soft graper is very simple and provide another promising solution. And there are many challenges exist at a different scale, let alone for multi-scale. At the macro scale, the grouping of three-dimensional objects, the main challenge lies in that the graper must be soft enough to facilitate intimate contact between the graper and the three-dimensional objects, but it needs to be stiff enough to support the high load while graping. At the micro scale, the main challenge lies in that to achieve weak enough interaction between the graper and the micro objects to facilitate reliable delivery. Some early attempts exploit the releasable caging by the jamming effect of the granular material. In this design, they put some granular material in a plastic bag. When this bag is filled with air, it's in the loose state and can conform to the three-dimensional object. While the gases are evacuated, the particles squeeze each other and the whole graper become very stiff and can grip the object. Or another design uses the controllable expansion and the contraction of the origami structure to grip the three-dimensional objects. These two designs work very well for three-dimensional macro-scaled objects, but they are unable to dispose planar or small objects. The graper designs based on controllable adhesion is very suitable for planar material, and by some deliberate design, they can also handle three-dimensional objects. For example, the inflatable soft adhesive membrane, or the load shearing by a stiffer backing layer and a soft adhesive layer. But they are at the cost of the adhesion strength and can also not dispose of the small objects, especially when the alignment accuracy is required, such as in the assembly of flexible electronics or micro LED chips. Here we propose a universal assembly graper design based on the chip memory polymer. This illustration shows I want to hide this. Okay. This illustration shows the gripping and release process. The gripper is a simple chip memory polymer block, and the SMP can be actuated into soft state by the outer stimulus, and we can embed the target object into the SMP gripper. The SMP can become stiff upon removal of the outer stimuli, and it can keep the deformed shape and lock the objects to grip it. After moving the objects to the destination, we can use the outer stimulus to drive the shape memory, to drive the recovery of the original shape of the SMP, and it can the shape memory shape memory effect can drive the release of the objects. Okay, here is a video shows some of the demonstrations. Here's the basic working principle. This is a polymer SMP block, and we hit it, it will become soft. And we can embed the object into the SMP gripper. After cooling it down, it can keep the temporary deformed shape and grip the object. After moving the object to the destination, we can reheat it, and the shape memory effect will of the object. We can scale the SMP block down to dispose of the objects at different scale and of different geometry. Here as a simple demonstration, we use a heating gun to drive the release of the object. Here, the heating gun will drive the shape recovery of the SMP block, and we can further scale it down. Scale it down to for the transfer printing of the steel server arrays with a diameter of 1 millimeter, 500 micrometer down to 300 micrometer. Yeah, we can. This is the transfer printing process of the steel server arrays with a diameter of 300 micrometer. Yeah, we can continue to scale the gripper down to manipulate the microparticles. So those are the demonstrations. Let's continue with the details. We choose a thermally-triggered SMP as the gripper material. This SMP has a low glass transition temperature of about 45 degrees centigrade, and the store modulus can reduce its grade dramatically through the TG, and below the TG, the SMP is in a stiff state with storage modulus of more than 2.5 gigapascal, below 25 degrees centigrade, while above the glass transition temperature is in a soft state with the storage modulus less than 2.5 megapascal. And the SMP can sustain very large elongation before failure at the source stage. And here shows the temporary shape locking effect. We embed the steel server into a SMP block. After cooling is done, the steel server is knocked into it. Then we reheat it. The SMP will recover its original shape and drive the release of the steel surface. And the shape recover is the SMP can fully recover its original shape under really large compression ratio. The recovery ratio can be more than 99%, even at a large compression ratio of 16.5, and it can also fully recover the original shape under repeated compression. Then we carried out pull-out tests to see how much load the gripper can sustain on different macro-scaled geometries. The SMP block can yield very large grip force. For example, the grip force is about 23.6 Newton on a small steel surface with a diameter of 10 millimeter. That's equal to 300 kilopascal on the cross-sectional area. And for any larger objects, we can also handle it with the SMP gripper by embedding the surface reliefs of the objects into the SMP gripper. Here, we grip an land platform by embedding the screw on the platform into the SMP gripper. And the SMP gripper can also be applicable to planar surface, be it rough or smooth, and the equivalent adhesion strength can be 113.9 kilopascal on the smooth glass, comparable to the GQ adhesive 100 kilopascal. And even though the surface is rough, the adhesion strength is not reduced obviously. And we can also scale the gripper down to for the transfer printing of meso-scaled several arrays with very large quantities. Here we prepared the steel surface arrays on the Kaplan tape, and we embedded the steel surface arrays into the SMP gripper and transferred it from the Kaplan tape into the SMP gripper. The embedding can not only provide a large grip force for reliable gripping, it can also constrain the objects from the unwanted lateral movement to keep the predefined arrangement. That's really important in transfer printing, especially high alignment accuracy required. Using this gripper, we have demonstrated its transfer printing of the steel surface arrays with 1 millimeter, 400 micrometer, and 300 micrometer. Because after releasing the three-dimensional objects, for example, the steel surface has very little contact with the gripper, so the adhesion is very low. This makes it possible fast to print the three-dimensional objects such as the steel surface onto some unconventional substrates, such as the forearm of a person and on the leaves. And we can further scale it down to handle highly irregular iron particles. Here we transform the arrangement of the four highly irregular iron particle from the bigger rectangle into a smaller rhombus, and it can also maneuver the particles as small as 10 micrometer. Yes, for those three-dimensional objects, the contact is very small, so the adhesion is very low after release. But for some planar objects, for example, the ALD chips, the contact between the objects and the gripper is relatively large. The adhesion will prevent the release. But for our gripping scheme, we do not rely on adhesion, but the embedding of the objects. So whenever the adhesion causes trouble, we can get rid of it simply by surface treatment or introducing some surface roughness. Here we introduce the surface roughness by molding the sandpaper, and it can be seen that the adhesion is reduced greatly, while the gripping force is not influenced obviously. This enables reliable gripping and release. By the local heating of a laser, the SMP can release the LED chips selectively. And here we this enables program printing of the LED chips. By scanning of the laser heating, we can print the LED chips onto the substrates with the desired pattern, as shown here. Here the LED chips lighted on the probe station. Because the SMP has a very low glass transition temperature, the heating power is very low, as low as 125 microwatts. So the performance of the LED chips are not influenced obviously, and the current and the voltage curves are nearly identical before and after transfer. So finally, we come to the summary. In this work, we have proposed a novel universal paper applicable to multiscaled arbitrarily shaped objects, and it's a simple design of a SMP block. The gripping is realized by the embedding of the objects and the temporal shape fixing effect of the SMP, and the release is enabled by the shape memory effects of the SMP. We have demonstrated the capabilities of the gripper by the gripping, transporting, and placing of macro-scaled objects, and the transfer printing of meso-scaled steel arrays, and the manipulation of microparticles, and the selective and the patterned transfer printing of the micro LED chips. This is really promising in the fabrication of micro LED display panels, and we have found some companies to collaborate with us to continue move this scheme into industry. But we need to further work on the response speed of the gripping and the release process. And I also want to thank my professor, my supervisor, Professor Jizhou Song, for his direction, and my colleagues, also the mentees participated in this work. And Mr. Shun Zhang and I contributed equally to this work. So thank you for your listening. Thank you very much. I'm Changhong LINGHU from Zhejiang University. Thank you.
Thank you, Changhong. So I have questions. Yeah, I got a question from Salting. Hello, Salting. Yeah, you have a question.
Yes, thank you for very comprehensive and thorough presentation. The content is also very interesting. So to my knowledge, actually one challenge in the field of software robotics is small scale robots or actuation. And I see that actually demonstrates some capability of grabbing microscale or even mesoscale particles using grippers. One of my questions, I see your first few demonstrations, the entire structure of the gripper is still pretty large. But if you think about the practical environment, in some cases, the environment is also can be very small and constrained to a small environment. So do you have any solution or answer to such kind of working scenarios?
Yeah. Thank you for your advice. We have discussed also with my professor, supervisor, Professor Jizhou Song, and my mentees. The constrained environment, for example, we usually will encounter this in in medical devices in our body. So in that time, we can also make it using some smart materials. You know, the SMP is not constrained to ceremony triggered. It can be also light triggered, and we can also combine some iron particles or some other magnetic particles into the SMP. So we can drive the shape recovery process by the magnetic field. This method can be used in the constrained environment. Thank you.
I see. Thank you. Thank you.
Okay. Next question is from Guo Yong.
Hi, Linghu. Very nice talk. And I have two questions. One is, I saw your slides, and do you need some special? I mean, the object should be some special shape that could be use your grapper to take them, or if for some complex shape object, will they destroyed during the graphing process?
I didn't fully catch your meaning.
I mean, in your slides, the object is in very simple shape. It's like a sphere or a cube. And I'm curious if could you grab some more complex object? Will they destroy it during the graphing process?
I haven't tried that. But I think for highly irregular objects, you mean at the macro scale? For micro scale, we have manipulate the highly irregular particles. But for the macro scale, we have tried to test the grip force on some basic geometries, those simple geometries. But for the highly irregular objects at the macro scale, I didn't carry out some experiments. I think it shouldn't be a problem. We grip by the embedding of the objects. So if the object is highly irregular, I think it will form some locking. It will form some locking at the same time, which is helpful to which is very helpful to increasing the grip force.
Okay. And another question is the lowest. What's the lowest?
Yeah, I can
you
hear you
show
now.
A diagram, but the maximum one is gigapascal. I'm curious. I'm sorry.
Yeah, I can hear you now.
So you sure is 0 gigapascal? I was wondering what's the exact number of the lowest storage modulus?
Yeah, the storage modulus is 2.5 gigapascal at 25 degrees centigrade.
I mean the lowest one. Yeah. What's the value of the horizontal?
You mean in its soft state? In its soft state. Yeah. It's less than 1 megapascal when heated to 120 degrees centigrade.
Okay.
Yeah.
Well, will it be a problem to grab some, for example, a very soft hard gel? Could I use grapper?
You got the point. Yeah, this is a big problem. Here we must embed the object into the SMT. You know, the SMT is not, in fact, it's not that soft. it's more stiff compared to the hydrogel, so it cannot work to grip some very soft materials like hydrogel, or for example, grab the egg, boiled egg.
Okay, thank you.
Hello, Linghu. I have a question.
Hi.
Yeah. So, if the target subject is too sharp, so
Too
does
sharp,
that
yeah.
object cause fracture or damage to your gripper?
I think there should be, but in our experiments, we tried to avoid this kind of condition.
Okay. Yeah. So, did you observe any fracture case in your?
But in our experiments, we repeat the pull-out test with the thin gripper, with those geometries, even the cubic and the steel plate. We didn't observe the fracture.
Okay, I see.
Yeah.
Okay, I see. Thank you.